For decades, the American V8 engine was a simple concept with a simple compromise. You got enormous power, but it came at the cost of terrible gas mileage, high emissions, and a reputation for being heavy and relatively crude. People often look at the V8 today and say it's a dinosaur, a simple gas-guzzling relic destined for extinction, clinging to life out of pure, stubborn nostalgia. They are wrong. This perspective misses one of the greatest stories of modern mechanical genius. What if I told you that the engine in a new Ford Mustang GT makes 3 times the horsepower of its smog-choked, inefficient 1970s counterpart, runs cleaner than the power plant that charges a modern electric vehicle, and can drive 200,000 miles before needing a major service? That's not a relic, that's an engineering miracle. The modern V8 is not a compromise. It's a triumph of conflicting requirements, a masterpiece of extracting massive power while meeting near-impossible global emission standards and delivering mile-long reliability. The resurgence of American horsepower, the incredible performance of cars like the Chevy Camaro, the Corvette, and the Mustang is the result of a silent, intense, high-stakes war fought between the engineers at Dearborn and Bowling Green. These companies, Ford and General Motors, didn't just build faster engines, they perfected the V8 through 2 fundamentally different and fiercely competing engineering philosophies, the Pushrod LT versus the overhead cam Coyote. Each architecture represents a unique path to achieving the impossible, and understanding the core differences shows you just how brilliant these engines really are. Let's start with Chevrolet. For over 70 years, GM has clung to the Pushrod design, an engine architecture that traces its roots back to the 1950s. To the casual observer, it seems like a stubborn refusal to modernize. But for the engineers at GM, it's a commitment to compactness and simplicity, and that simplicity has hidden advantages. In a pushrod engine, the camshaft, the component that dictates when the valves open and close, is located deep within the engine block. The valves in the cylinder head are opened via long rods called pushrods and rocker arms. Why does this matter? By keeping the single camshaft in the block, the LT engine is physically tiny and lightweight for its displacement. It has significantly smaller cylinder heads than its Ford rival. This compactness is crucial for sports cars like the Corvette and Camaro. It allows the engine to be mounted lower and further back in the chassis, creating a lower center of gravity. This translates directly to better handling, faster cornering, and a more balanced car, which is absolutely vital when chasing lap times. This architecture proves that sometimes the oldest solution is the most elegant, provided you can overcome its historic flaws. And overcoming those flaws is where the real engineering miracle of the LT takes place. The power secret isn't in the classic architecture, it's in the modern accessories. The key is direct fuel injection (DI). In the old days, fuel was sprayed into the intake port before the combustion chamber. The LT, however, sprays fuel directly into the cylinder under immense pressure, up to 2,900 psi. This allows engineers to run much higher compression ratios and achieve significantly more precise ignition timing than ever before. This precision extracts far more power and efficiency from every single drop of gasoline. It cools the combustion chamber and prevents the pre-ignition that used to limit performance in older V8s. And because a modern V8 must also be an eco-warrior, the LT utilizes a stunning piece of technology called cylinder deactivation, which GM brands as active fuel management, AFM, or dynamic fuel management, DFM. When you're cruising on the highway using minimal throttle, 4 of the 8 cylinders literally shut off. This isn't just cutting fuel. Using oil pressure, the system collapses the lifters, stopping the intake and exhaust valves from opening. The engine effectively becomes a temporary 4-cylinder, instantly boosting highway economy to 25 or even 30 miles per gallon. The Pushrod V8 is a flexible, highly efficient machine disguised as a muscle car beast, proving that high power and high efficiency are no longer mutually exclusive. Now, let's look at the other side of the war. Ford took the exact opposite, more technologically complex and arguably more ambitious path. The advanced dual overhead cam D, DOHC design, famously known as the Coyote V8. DOHC means 4 separate camshafts, 2 for intake and 2 for exhaust, are mounted right on top of the cylinder heads. It's a wider, larger, and more complex engine than the LT, which can present packaging challenges. But DOHC unlocks the single most important key to high RPM power: unrestricted, precise airflow. Without the weight and inertia of pushrods, the valves can open and close much faster and more reliably. This allows the Coyote to breathe deep and scream to a much higher redline, often 7,500 RPM or more, giving it the sound and specific output of a race engine. The core technology behind the Coyote's high-revving nature is twin-independent variable camshaft timing, ti-vct. This is the real magic. Unlike old engines that had fixed valve timing, the Coyote's computer can instantly change when both the intake and exhaust valves open and close independently, hundreds of times per second. At low speeds, the timing is optimized for low-end torque. At high speeds, the timing changes instantly to optimize for maximum horsepower. This means the engine is literally transforming its performance characteristics in real time, giving the driver the best of both worlds: comfortable low-end grunt and explosive high RPM power. Ford also attacked the efficiency and longevity problem with a revolutionary injection strategy called dual injection. Ford uses a 2-pronged attack. It employs direct injection, just like the LT, for power and cooling the combustion chamber, but it also keeps the traditional port injection system. Why use both? Port injection helps with low-speed smoothness, and crucially, it sprays fuel onto the back of the intake valves. This constantly washes away the carbon deposits that are a well-known side effect of direct injection systems, balancing raw performance with long-term reliability and lower maintenance. The true miracle for both of these engines, however, isn't just raw horsepower. It's the fact that they can do all of this while passing the world's most stringent emissions regulations. The engine's computer, the ECU, is a piece of hardware that is 1,000 times faster than the computer that sent man to the moon. It monitors oxygen sensors, NOx sensors, and exhaust temperatures, making micro-adjustments to the air-fuel mixture hundreds of times per second to ensure the exhaust gas is perfectly formulated for the catalytic converters to clean. They run within an infinitesimally small operating window, a hair's width away from generating illegal levels of pollution, yet they deliver incredible performance. That precise, continuous, high-performance cleanup operation is the unseen genius behind every modern V8. These engines matter not just for fun, but for context. They prove that the internal combustion engine is not a caveman technology waiting to die. It is a constantly evolving, high-tech machine pushed to its absolute mechanical limits. Both the Coyote and the LT represent the pinnacle of mechanical engineering, extracting every ounce of power and efficiency possible before the inevitable market shift to electric power. Ultimately, the V8 survives not out of mere nostalgia, but out of engineering genius. The Pushrod LT is a masterwork of size, low center of gravity, and elegant simplicity, winning on efficiency and packaging. The DOHC Coyote is a masterpiece of high RPM breathing, valve control, and raw specific output, winning on high-end power and a screaming redline. They are two competing masterpieces, both defying the constraints of modern regulations while delivering supercar performance. These are not relics. They are the final and perhaps best generation of gasoline V8s the world may ever see.